Hey, so these are the beginning of the notes for the next unit, which is called Mapping the Earth. So the note packet actually starts out right here talking about the shape of the Earth. So you probably have heard people be like, the Earth is flat. Well, from your limited perspective, essentially, yes, but on a much larger scale, no. So how do we know it's round? Well, ships appear to sink as they go over the horizon. So if you ever watched a boat go out to sea, they get smaller and smaller and smaller as it gets farther and farther away, but it also starts to disappear. That's because it's going, so you can see the boat, and it starts to disappear from the bottom to the top. So like my finger is the mast of the boat, it starts to disappear from the bottom to the top as it goes over the curve of the Earth. A lunar eclipse casts a curved shadow. So a lunar eclipse is just when the Earth casts its shadow onto the moon. So let's check out one more object real quick. A moon. All right, here's my moon. So in a lunar eclipse, it would be if my face is the sun, if my glowing radiant face is the sun, it would go sun, and then Earth, and then moon would be behind the Earth, so our shadow would be on the moon. And when that happens, we get a curved shadow. And the only way you can get a curved shadow is if the object's casting it as round. You're like, wait a minute, this is round. This will cast, it's round, but it's flat. So but head down, it would cast a roundish shadow, right, from the side. Thing is, though, we never see a shadow that looks like this on the moon. It's just like a flat line across the moon. Like, we never see this. It's always, no matter what angle we look at it, it's always a curve. And the only way to get a curve from any angle, from anywhere, is if the object that's casting the shadow is round. So we knew those ones for a while. This one is relatively new. You actually weigh more at the poles than you do at the equator because you're a little bit closer to the center of the Earth at the poles. So let me get another object. So your weight is basically how much gravity is tugging on you, and the closer you are, the more gravity tugs on you, and the more you weigh. So the idea here is because Earth is actually spinning, or we're going to use the scientific term rotating, because Earth is rotating so fast. It's like if you ever been on one of those spinning rides that spins you around and around and around, and like it presses your back against your seat. I don't like those at all. But if you've ever been to one of those, you've experienced this force. It's the same force that actually, because the Earth spins so fast, it like squashes the Earth a little bit. And the end result is if you're at the pole, you're a bit closer to the center of the Earth, and you get tugged on more by gravity. Fourth, we have your angle to Polaris changes depending on your latitude. You're going to do an astronomy lab where you get to virtually go to different places on Earth and actually measure this angle. Your angle to Polaris, which is the North Star, changes depending on your latitude. So it's the North Star because it's over Earth's North Pole. It's way, way, way out in space, but it just happens to randomly be the star that's over Earth's North Pole. And no matter where you are on Earth, your angle to the star, it'll change depending on how far north or south you are. And the only way for that to happen is if the Earth is in fact round. Actually, we'll get two more objects. I'll show you. Okay, so here's my Earth. Polaris. Let's see. We're going to be way, way, way over there, somewhere over the North Pole. Watch this. This is pretty wild. This is my horizon line, which is what I can see. And then this is going to be my angle to Polaris. As I go north, that angle gets bigger. As I go south, that angle gets smaller. As I go north, this is my angle that's pointing off to Polaris. That gets bigger. As I go south, it gets smaller. The only way for this geometry to happen is if the Earth is round. It's basically just geometry. That's really all it is. We actually knew a lot of this for thousands of years because the ancient Greeks were pretty good at geometry. It's just it didn't really vibe with people's everyday experiences, so they just didn't believe it. But the math was all there to prove it a long time ago. All right. Oh, and finally, we got pictures from space, which are absolutely beautiful. This one is taken from one of the Apollo missions, where those are the moon missions. The first went to the moon. So we got pictures from the Earth, from space, and well, it's round. Also, this little diagram right here just shows you how squashed the Earth is. It's not squashed too much because it spins so fast. Like, I really squashed this ball, but it's really not that squashed. Like, it's pretty round. The difference here is only 42 kilometers, which is not a lot when the Earth is 12,000 kilometers across. So it's pretty much still a perfect sphere, but just not exactly a perfect sphere. All right, so basically from this, the takeaway is you got to know these 5 ways that we know Earth is round. All right.